Okay, happy Monday! Start of our next week of videos and remote learning. We are on 4.5 part 2. So you guys, what we did for the first part of 4.5, we're going like kind of out of order as far as like the homework problems go. But we did that 3-part definition, right? About continuity at a specific point, at a point C. And now we're kind of talking more about that like continuity in general idea, but in a much more formal way. So I know that you guys understand with continuity, oh, if I can just trace along my graph and never have to pick up my pencil, then I'm continuous everywhere. And we love graphs that are continuous everywhere, that we don't have to pick up our pencil on. It also becomes important too when we get into calculus more, we start talking about where we're differentiable at. So, I mean, there's going to be a part like that we love when graphs are continuous. So, things that we kind of know about continuous, things that we know are continuous, would be polynomials, right? Like, the most basic polynomial would be a constant function, just a horizontal line. You can go everywhere across that, never have to pick up your pencil, and you just know that it's a type of polynomial. You could even name it a constant function, but typically we just say polynomial. And we know linear functions are continuous everywhere. A diagonal line, whether your slope is positive or your slope is negative, and no matter where your y-intercept is. And then quadratics would be the next one, like if you kind of think going up in degree, and they're continuous everywhere. And then our cubic functions, our John Travolta graphs, right? All of those kind of graphs with like higher and higher degrees, those are continuous everywhere. So we love polynomials. And it's going to be important that we can like state what kind of graph we have and where the continuity is if we're talking like as a whole. And we love absolute value functions. Our absolute value function is going to graph a v. And you can go everywhere on your v and never have to pick up your pencil. So we love absolute value functions. So anytime we have those, we can just kind of state that, and like it's a general like theorem that you're stating in words. So the other thing, kind of extending that idea, like kind of what we did with limits, that's why we do continuity after we do limits, is that if we have a sum of two continuous functions, and then I get lazy and start just abbreviating continuous with CONT, I think Kearney does that as well, then we know a sum of two continuous functions would also have to be continuous. Or that a difference, if I subtract two continuous functions, that also has to be continuous. The difference of two continuous functions is continuous. So actually this should probably be is instead of are.
Forgot your grammar.
I know, right? And that if we multiply two continuous functions together, that new answer for the product is continuous. So make sure you're writing this down, these statements down, okay? But with the correct grammar that I'm fixing now. And then as long as it's a quotient of two continuous functions is going to be continuous as well, except where the denominator would equal 0. Because we know if denominators equal 0, we have a continuity issue there, right? Any spot where denominator equals 0 is either a point disco or a vertical asymptote. And so we know like we kind of have like a problem issue there. So these are our 4 basic operations in math, right? Add, subtract, multiply, divide. And so we're kind of just extending that idea into the continuity idea. So make sure that you kind of have that all written down. And then let's kind of talk about where we might have problem areas and how we're going to kind of fix that when we use some words with continuity. Because we, just kind of like fix it and make it work. So our problem areas that we're going to encounter, of course, I was just kind of saying, would be where you have denominators that would give you division by 0, right? Because if we have division by 0, then we either have a point disco or we have a vertical asymptote. And then kind of some other spots that we might have problem areas would be a negative underneath a radical. And I'm going to say under an even root, right? Whether it's a square root, that's probably the most common, or a fourth root. If it were an odd root, a cube root, that wouldn't matter. You can take the cube root of a negative, it just gives you a negative answer. So it'd be underneath the even root. This is also connected to domain. Continuity is very linked in with domain. And then some other problem areas. Well, actually, I think that's it, right? Division by 0 from a point disco or vertical asymptote, or a negative underneath an even root. So the way kind of that we fix that, or that we kind of talk about it, is we use this language. Oh, on the very end we say it's continuous within its domain. So that phrase, you're going to like keep hearing like over and over and over and over again.
The other issue would be if you had logarithms. You can't
yeah.
have zero or negatives for inside logarithms.
So
I don't think any of those will appear on your homework, but
think so
it is another problem area though.
So with logs, we'll just add it right here. We'll have to say positive of part. Like whatever you're taking the log of would have to be positive, right? It would have to be greater than or greater than, not even equal, just greater than 0. Because you can't take the log of 0 either.
It would be just like you're finding a domain.
Yeah, all linked
Exactly
to what we've done
like
with
it.
domain. So all totally like interconnected there. Okay, so kind of the way that we take care of that is we add this little phrase about, oh, it's continuous within the domain. So if I gave you guys a square root function, and the easiest square root function we could think of would be f of x equals the square root of x, we would say, oh, square root functions are continuous within their domain. And then if we actually needed to list out the domain, then we would take the radicand and set it greater than or equal to 0 like we did back in the last packet and we did and tested on already. But if we're just talking about like the generalized idea, if it's an even root, and most of the time it'd be a square root, we just add that little phrase about, oh, we're continuous within the domain, and then we go, oh, everywhere within the domain we're going to remain unbroken. If you think about like the parent function graph, right, you have your starting point at 0, 0, and don't you slowly increase to the right. I can trace along that fine. I just can't go over here because there's nothing over here. It's not part of my domain. There's nothing to graph there. It's like I answers there. And then another one is if we have a rational function. So if we have a rational function where we're going to have a denominator with variables where we would get some division by 0, we just say, oh, rational functions are continuous within their domain. And then we're just kind of like covering the bases and saying like, we understand there's like these problem issues, but as long as we stay within the domain, we're going to be able to trace along the curve and remain unbroken. So if I gave you the most basic rational function, wouldn't this rational function be continuous within its domain? And its domain would be from negative infinity up to 0, union with 0 up to positive infinity. So everywhere, as long as we're not at the vertical asymptote of 0, we're fine, right? Like everywhere else we're fine. So if we kind of add this like little phrase, we're covering our bases. If we had the rational function f of x equals x plus 1 over x squared minus 1, this is just a little bit of review from the last packet as well. Well, yeah, that's a rational function, and maybe you instantly see in the denominator, ooh, we can factor right there, and that's correct. We can't factor because we have a difference of squares. And if we factor in our denominator, so we can just analyze a little bit better our domain, we know we have two domain issues, at positive 1 and at negative 1. But you guys remember that if you have something that goes away with the factor on top, that this is not a vertical asymptote spot, right? Wouldn't this be a point disco at negative 1? So just kind of reviewing that, the graph really behaves like the graph of, I'm going to say y instead of f of x, 1 over x minus 1. It behaves like this graph. But there's this point discontinuity going on at negative 1, and if you want to know the y that corresponds with that, you actually plug it into what the graph behaves like. So wouldn't negative 1, if I plug it in, negative 1 minus 1 give me a negative 2? So the output would be negative 1/2. So there's a point disco at negative 1 comma negative 1/2. And then there's a vertical asymptote where it doesn't factor off of anything at x equals positive 1. Remember, vertical lines go x equals a number, and if you set that part with the factor x minus 1 equal to 0, or find where it doesn't equal 0, you would add the 1 over. So there'd be a vertical asymptote at positive 1. So even though it behaves like this simpler graph, you guys, it's not this. It started here. So wouldn't our domain be all of our x's that would equal negative infinity leading up to negative 1, where our point disco is? We can't include that. That's an open dot there. Unioned with negative 1 up to positive 1, where our vertical asymptote is. Unioned with 1 to positive infinity. But other than those two spots, we're continuous everywhere else. So the idea is, oh, okay, if we just say it's a rational function and rational functions are continuous within their domain, we kind of cover that a lot of times for what we're doing in this section, you don't even need to state the domain. It's just trying to link back to make you understand that it's connected to the domain. Okay?
Yeah, so guys, like my first couple of years of teaching this stuff, I absolutely hated it. I'm still not a big fan of it, but like I understand the importance of it now with calculus. Okay? You're not going to see a whole lot of purpose for actually doing this, all right, until next year. Actually, when you look at your Wednesday's homework, I think, or Tuesdays.
Mm-hmm.
Anyway, whenever you're doing the intermediate value theorem, okay, what's going to be important is that it's continuous either on this interval or part of this interval or part of this interval. Okay, I always call this like a stupid loophole.
That's a good way to.
I was like, oh yeah, it's continuous everywhere within its domain.
Mm-hmm.
All right, because if you check this out, like if we were to actually draw this graph, okay, we knew there's a vertical asymptote at 1, and we know there's a point disco at -1, -1/2. Okay, so there's a hole there. Horizontal asymptotes at 0 here. Guys, if we were to draw this, okay, I am continuous from -infinity to -1. Okay, I can draw that without lifting up my pencil. Here, I'm going to lift up my pencil. Okay, so it's not continuous, obviously, at -1.
The function's also not defined there.
I am continuous, however, from -1 to +1. Okay, and then over here, I'm continuous from 1 to infinity. Okay, because I can draw each one of these sections without lifting up my pencil, so it's continuous. Okay, we don't really care about that, but during our theorems, you're going to be like, oh, from 2 to 3, we have to be continuous on that interval, and this is going to be our rationale. Well, it's a rational function, it's continuous on these 3 sections, therefore it would be continuous from 2 to 3. Okay, so that's going to be like the long term why this is useful. Short term, you won't see that while you're doing your homework tonight. You'll be like, this is just a lot of words.
Yeah, it doesn't seem very pre-calc mathy. It seems like a lot of words. The other nice reason to learn some of this stuff is it makes you good at stating what kind of function you have. At just like knowing the vocabulary and the names of the functions. So that's also like another reason that we keep it in, even though to you guys it probably seems irrelevant. And then the last one before we actually get to examples, I am going to say what the number is. It's theorem 8. And we're going to write it down really formally. So it says, if G is continuous at some C value, and F is continuous at G of C, then F of G of C is continuous, which is the composition. And we even add some limits in there, and then I'll explain to you like what you're going to write down, okay? Because you're not really going to ever regurgitate this theorem. But the limit as x approaches C of F of G of X equals F of G of C. Is then the first thing that we try with limits, direct substitution. So as long as we're continuous at a specific point on the inside function, and we can work from inside out on composition, this is saying, oh, then we're continuous when we compose functions. So what this theorem really says, and what you guys are going to actually write down on homework, is that the composition, remember composition is like a 5th operation on functions, that the composition of 2 continuous functions is continuous. So if you know individually, and you're working inside out, that the smaller functions are continuous, then when you compose them, then you can say, oh, the composition of 2 continuous functions is continuous. So, like I said, the homework is like really weird for this section, but try to really watch the video. Like, watch me go through one, then the next one, try it on your own, put it on pause, then like watch and see how your explanation goes in words, if it matches my explanation. And don't get creative, like try and stay exactly how we're wording it on the video to how you're gonna word it on your homework. So we're actually ready for some examples. And you guys are gonna see a whole bunch of new Greek letters. So a lot of this stuff, they're doing that like crazy notation that the packet likes to do, and they're using the Greek alphabet to denote some things. So it says, prove that. By the way, prove that means it is true. You're just proving that it's true. Prove that, and then they have this symbol. So this is the symbol for phi. It's from the Greek alphabet. I get lazy and I like to draw it where I don't pick up my pencil and I just like kind of loop it straight down. Mr. Herney, I think, draws it more like this on a diagonal. Okay, so prove that phi, which is assigned for every element of its domain x, the rule big square root of x squared plus 1 over x squared minus 1 is continuous. And again, I'm being lazy and just doing CONT for continuous. So there's nothing mathematically that you're going to do here. It's a whole bunch of breakdown and writing it and stating how you know individual pieces are continuous and putting it all back together. A whole bunch of words. So just kind of roll with it. So first thing is, just like we did early on in the packet in sections 4.1 to 4.3, you're probably looking at this going, I hate this. I'm going to write this like this. Function notation. Phi of x is equal to big square root of x squared plus 1 over x squared minus 1. Well, right now, that's not a function that you probably recognize or could name or state why it's continuous or not. So maybe let's break it down. So what I see, I don't know if this is what you guys see, but what I see is I go, well, I see kind of like this inside-outside idea. I see a rational function on the inside because I have x squared plus 1 with some stuff with the variables on top. That's a polynomial on top, and another polynomial on bottom, x squared minus 1. And if I put them together, I see a rational function. And then I'm taking the square root of the rational function. So remember when we were decomposing functions and we were like breaking them into small, simpler pieces and saying how to compose them back together? That's why we did that, is also for this section. Oh, so let's maybe define f of x as the rational function x squared plus 1 over x squared minus 1. And we just went through this. Aren't rational functions continuous everywhere within their domain? And we could just state that. You don't even need to tell me that the domain is all the numbers except positive 1 and negative 1. I mean, yes, this would factor the difference of squares. They would both be vertical asymptotes because nothing would cancel from up here, but you don't even need to say that. You just need to be able to say in words, oh, rational functions are continuous. And we're trying to make things easy, like abbreviate continuous the way Herney and I do. I always do with a slash within their domain. Cool.
Functions are fun.
Functions are fun. I'm going to say that outside is going to be g of x. And g of x is, okay, well, don't I need to get this big square root around that rational function? So what do I want g of x to be? The square root of x. So if I were working from inside out, I'd be plugging all of that whole rational function in place of the x. And that's another function we should be able to name. Oh, it's a square root function. And we know, because it's an even root, we wouldn't want a negative underneath here, right? Because if we had a negative underneath here, we would get i's. So really we want the domain to be from 0 to infinity. But we don't even have to say that. We just say, oh, square root functions are continuous within their domain. Don't you guys like this? All these words? This is why Mr. Herney makes me teach these lessons, because he doesn't like words. And now you just have to say how to compose it back together, because you could pick whatever letters, honestly, you want up here. And so you have to state how to get back to the original, more complicated function, which is defined as phi. Okay, so therefore, phi of x would equal, in the way I defined it, right, we work from inside out, so this was the inside, this was the outside, so it would equal the composition of g of f of x in that order, so I'd really get back to the whole great big thing. And that theorem that's still on that board, that theorem 8, remember what I told you the important part was? I put a star by it? Is that the composition of two continuous functions is continuous. So as long as you can state that these are continuous within their domain, then you can say the composition of two continuous functions is continuous. You're not graphing anything, you're not doing it really any math, you're decomposing it and giving us these rules and these theorems along the way. That's all you're doing to prove that something is continuous. And that's what you did at the very beginning of the homework for section 4.5 part 2. Okay? So let's do another one. We're going to, again, show that it's continuous with other words, but then we're also going to graph it. And the reason that we're going to graph it is because the second part of your homework says to go back and like graph for numbers 11 through 18, problems 1 through 8, which you already did the words on. So we're going to kind of blend that into one big example. So example 2 says to show that, if you're proving that or you're showing something, that means it is true. You're just proving that it is. And I'm going to do a different Greek variable this time. So another one that we use kind of common is, what did we say, Mr. Herney? This one was psi? PSI?
Psi.
So it kind of looks like a pitchfork. I don't know, that's what I think of, like a fork. So you have like your line and then this little like curve on top, or like a capital Y, but like there's an extra little extension. And psi is defined so that every element x in its domain attaches to the rule, that's what this arrow is, or maps to the rule, the absolute value of x squared minus 1, close absolute value bars, and then behind it another minus 1. So we're going to show that that rule is continuous, and then draw its graph. Okay? So remember, when you're in this crazy packet and they're doing this like wonky notation, you just turn it into function notation. So you start to feel more comfortable and feel like, oh yeah, I know what I'm doing. Okay, so psi of x in function notation equals, so the arrow's like the equals, the absolute value of x squared minus 1 inside of my absolute value bars. So make sure and extend your absolute value bars long so you realize like that's a part that's a grouping symbol, and then behind it is a minus 1. All right, so let's start breaking it down. And there's maybe more than one correct way to break it down, but again, I'm going to explain maybe the most efficient way and what I see. So I see a quadratic is a type of polynomial on the inside of the absolute value bars. Absolute value bars are like a grouping symbol. So kind of when you have parentheses or some sort of grouping symbol, a square root sign is a grouping symbol, it kind of gives you that like inside piece. So I would probably think this was my inside function. And then my outside function would be that I have the absolute value with the minus 1 behind it. That's how I'm going to break it down. Because if I can break down those little baby steps and know that they're continuous, then I can say, oh, the composition of two continuous functions is continuous. It will not always be a composition. So I know that one on your homework, so I'm going to go like a little off tangent, sideways thing like I like to do. I know one of the ones on your homework, I'm guessing, it's number 7, is whatever the rule is. Let's use that phi. Let's say it's phi of x equals x, and it's multiplied with the square root of x. So if you were trying to prove that that one would be continuous, it's something similar to that. It might not be exactly that. You would say, oh, x is a polynomial. Y equals x, f of x equals x. That's a polynomial, guys. It's linear. Polynomials are continuous everywhere. And then you would say your other function, g, would be the square root of x. Square root functions are continuous within their domain. We just wrote that over here, right? Because this isn't composing it. It's not working it inside out. This one you would just say each one individually, and then you would say the product of two continuous functions is continuous because we're multiplying together. So it doesn't always have to be at the end that you put them back together with composition. This one at the end would say the product of two continuous functions is continuous. And then honestly, for this graph, you would graph it on your calculator, because you're not going to know any kind of transformation of a parent function for that. You're not going to be able to break it down like we're going to teach you how to break down this one with a chain of functions and work inside out because it's a composition. You're just going to have to flat out like do it on the calculator and know that it's a product of two continuous functions. Okay, so I'll kind of keep that up and go back to some things specifically on homework after we do this example. So this one is a composition. So I'm going to say f of x, the inside piece, is the x squared minus 1. That's a quadratic function. It's one of our easiest kind of polynomials. But the way that I'm going to say it is, hey, it's a polynomial. Polynomial functions are continuous everywhere. I don't need the little phrase within its domain. They're continuous everywhere, right? U-shaped parabola. I never have to pick up my pencil to draw it. So polynomials are continuous everywhere. And then g of x, well, this one is like that inside, outside, put it all back together with composition. So g of x would be that I want to plop this in here inside the absolute value bars and then subtract the 1 from it. So wouldn't I want g of x to just be the square root of x? So I would plop that whole thing for f in, and then behind it, after I close absolute value bars, a minus 1. Well, that's another simple function too that we know is continuous everywhere because that's absolute value function. So don't we just say, for this one sentence, absolute value functions are continuous everywhere. So now I've kind of said like those two easy parts. I'm going to erase and kind of move over here. And just like we did on the last problem, since this is a composition, therefore putting it all back together, psi of x would equal, well, the way that I wrote them down, I would have to compose them g of f of x, so this inside would plug into here, g of f of x. And the reason that I know that's continuous is because it's a composition. So that's that theorem 8. The composition of two continuous functions is continuous. Done. For the first part. So the part that we just did was this part. Show that it's continuous. Check. That's all the word stuff. Now we're gonna graph it. So this is something that is new that you guys haven't seen. And this graph, we would actually expect you to be able to do by hand. Okay? And again, a lot of what we're doing right now for this quarter is preparing you for calculus. So this is going to be more important, really, when you get into calculus than anything, but that's why we go over it at this level. So remember what we're really trying to graph is this final rule phi of x. So the way it was originally, or not phi, psi. Psi of x equals the absolute value of x squared minus 1, and behind it is a minus 1. So you'll kind of like get into the zone of these a little bit. We're going to do another one too after this last example. But the way that we're going to graph this, what I call it at least, I don't know what Mr. Herney calls it, is using kind of this chain of functions idea. Because we know like individually what x squared minus 1 would look like. And then maybe we can go to like the absolute value of it being taken and talk about that. And then at the end, talk about the minus 1. So we're still kind of using this like, oh, when we graph using a chain of functions, we're going to graph from the inside out, like we do with composition. Okay? So see if you guys can follow this. So it is going to be multiple graphs on multiple grids until we get to the very, very end. And the very, very end one is our final graph answer. So when you're doing this on your homework, I'll talk about which ones to do this way. So this first little grid I'm going to draw is going to be just graphing the very inside. So it's like I'm imagining graphing x squared minus 1. Oh, so if I had y equals x squared minus 1, I would know it was a U-shaped parabola. I would know that parabola is opening up. I would know that since it's in transformation form, it's just having the vertex at 0, 0 and shifting down 1. And I think a lot of you would instantly be able to see it. Sometimes it might not be in that transformation form, so you might want to think about factoring to know where the x-intercepts are. If you know the factors, set them equal to 0 and find the x-intercept. So if I factored this, it would be x plus 1 and x minus 1. Oh, so the x-intercept should be at positive 1 comma 0 and negative 1 comma 0. But even if I graphed it going, oh, it's just a U-shaped parabola shifted down 1, it opens up, so my vertex would be at 0, negative 1. Oh, the very important points would be going over 1, up 1. Oh yeah, there's the x-intercept. But you could also get it from factoring. And going left 1 and up 1. And then if I go over 2, I would go up 4. So over 2, up 1, 2, 3, 4. And going left 2 would also plot me up at 4, right? Parabola or symmetric. So this is kind of like my first part of my chain. This is that very inside part. And again, some of this stuff is new and really hinging on that you learn it at the pre-calc level so you're prepared for it at the calculus level. So then we got to think about, we're taking that graph and we're taking the absolute value of it. So you guys, your calculator can kind of do this, but it is really hard to distinguish what's going on off the calculator. You got to know how to do it by hand. So in the AP world, sometimes they'll do this. They'll go, hey, here's a function that you kind of know, and now you're going to take the absolute value of it. So the absolute value of this graph, doesn't absolute value mean anything that's negative would turn positive. So if I think about a graph, any parts of a graph that are negative would be below the x-axis. So what that is going to do to this graph is that is going to flip anything below the x-axis to be above the x-axis. So I still have the x-intercept at negative 1 and positive 1. And I still have my points at 2, 3 and negative 2, 3. But this whole portion is going to flip to be, instead of below the x-axis, to be above the x-axis. So that point that used to be down at 0, negative 1 is now at 0, positive 1. So it would look like this. This part still is curving up, just like it used to be, and this part is still curving up, just like it used to be. But this part that's below is now above. So it kind of has this like now sharp change of direction. Kind of looks like a W a little bit, but kind of like this weird W. And then the final thing, right, the final chain, we got like all of that part done, is to subtract 1. Well, if I subtract 1 on the end, that's a K. Subtracting 1 on the end, doesn't that move me vertically? So doesn't that take every dot that I have 1, 2, 3, 4, 5 dots, and take every dot that I have and moves me down 1 unit. So literally that's all you're gonna do. Oh, so this dot that used to be at 2, -2, +3 is now gonna be at -2, +2. And this dot that used to be on my x-axis at -1, 0 is now at -1, -1 down in quadrant 3. And this dot that used to be at 0, 1 is now at 0, 0 at the origin. And this dot that used to be at 1, 0 is now at 1, -1 down in quadrant 4. And this dot at 2, 3 is now at 2, 2. So it still has this part like this, and it still curves kind of like this for this W shape, but now the whole entire graph is shifted down 1. And this is my final graph of psi, or psi of x. So some of the graphs that you're going to have to do, you're going to have to know how to do by hand, using this chain of functions idea. There are a few that I'm going to tell you to just graph on your calculator. Like I said, I think one that looks really similar to this is number 7. If it's not identical to this, x times the square root of x, it's something like that, where it's a product of two things. So it's not a composition of two continuous functions is continuous. The end answer would be the product of two continuous functions is continuous. Okay? So let's go on to our last example. So again, I'm going to blend what you have to do on the homework into one big problem. But for the homework, the first chunk you do is like all of the wording and all of the theorems and say how you know things are continuous. And if you have a function that has a problem area, a rational function, you just say rational functions are continuous within their domain. If you have a square root function with an even root where you couldn't have negative underneath the radical, you just say square root functions are continuous within their domain. And if you have that little phrase, then you should be good. And then you just have to decide, okay, well, is it something complicated where it's a product of two things and a product of two continuous functions is continuous? Or is it a quotient of two things? Or is it a composition of two things? Those are typically the ones that you're putting together. Okay? So our last one, back to phi, is phi of x equals the absolute value of 1 minus the absolute value of x. Close the absolute value bars around the x, then close the big one around the whole entire quantity. So once again, we want to show that phi of x is continuous. That means it is. You just got to explain it all in words. And then sketch a graph. Okay. Well, this one definitely has that distinct like outside inside idea. So if it has an outside inside idea, let's decompose it first. Explain how to get back to the original phi with composition and in what order, and then we could say the composition of two continuous functions is continuous. So if I broke it down, maybe I'm going to switch it up this time. I'm going to say g of x for my inside. What I see for the very inside is I see the absolute value of this x. That's kind of what I see. Some of you might see the 1 minus the absolute value of x. That's fine too. Actually, maybe I'll do it that way. And then the big absolute value bars around it at the end. So I'm going to start with g of x being the 1 minus absolute value of x. Well, it's an absolute value graph, right? It's an absolute value function. It's absolute value of x, and then really this would be a reflected, so the v would be upside down, and then you would shift up 1 at the end, if I thought about what it looked like graphically. Oh yeah, like those are fine. They're continuous everywhere. I don't have to pick up my pencil, so I just say absolute value functions are continuous everywhere. So if it's a plain absolute value function, we love those, right? Big old love heart. If it's a polynomial, we love those. They're continuous everywhere, and you just say everywhere. But then I'm enclosing that with the whole absolute value bars that are around that whole entire quantity. So if I'm going to say that that one's defined as my f of x, then f of x would equal the absolute value of x. So all of this would eventually plug in here. But that's just another absolute value. So absolute value functions are continuous everywhere. Right? So therefore I just put them together. And the way that I define them to get back to my original phi of x would be f this time of g of x. So you have to say how to get back to the original. And that's the order I would go in, and I would say the composition of two continuous functions is continuous. So that's me taking care of this first part. Show that it's continuous, check. That's all the words. So now we're going to do the graph. So the graph part again, we're going to graph using this idea, because it is a composition and we can kind of do this like chain of using that inside out and graphing the inside and then the next chunk and then the next chunk and do multiple grids. We're going to graph that way for this problem as well. So if I thought about graphing this inside part, I was actually describing that already. Wouldn't it be, and sometimes it helps to like flip it around. Instead of maybe looking at it as 1 minus absolute value of x, maybe look at it like this, negative absolute value of x, and then behind that a plus 1. Right, the 1 is positive, this part's the part that's really negative. Oh, so it's absolute value, it's a v. Normally we would graph it like this, but doesn't this negative make us reflect over the x-axis? So it'd be graphed like this. And the slope essentially, because it's just two diagonal lines stuck together, would be down 1 over 1, down 1 over 1, down 1 over 1. But then we're adding 1 to it, so doesn't that shift that graph up 1 unit? It gives us that vertical translation. So instead of the vertex being at the origin at 0, 0, now it's at 0, 1. And instead of the point being at 1, negative 1, now it's at 1, comma 0 and negative 1, comma 0. Instead of being down at 2, comma negative 2 and 2, negative 2, negative 2, that's going to be for both the positive 2 and the negative 2, giving us the output of negative 1. So there's the first part. But now we're taking that entire graph and we're saying, well, we want to absolute value all of that graph. Oh, so just like we talked about in that last example, and this is important for calculus, if you take like an inside portion of a graph and now you're encompassing it in big absolute value bars, what it does graphically, think about what absolute value is. It's the distance that you are away from 0 on a number line. It's a distance. So it takes any negative answer and turns it positive. So on a graph, any negative outputs would be below the x-axis. Aren't that the locations of where the y's are negative? So any part that is below the x-axis has to flip to be above the x-axis. Any part that's already above the x-axis just stays there. So we're good with the dot at negative 1, 0. We're good with the dot at 0, 1. And we're good with the dot at 1, 0. But any negative y's have to flip to be above. Oh, so this dot that used to be at 2, negative 1 is now at 2, positive 1. And this dot that used to be at 2, negative 1 is now at negative 2, positive 1. So this one, you guys, really looks like a W because it's all portions of straight linear pieces. Where that last one kind of was like sort of like a sharp W with like these weird wonky changes of direction with the curves. So the final graph is really the graph that we want, which is representing the graph of phi of x. But we graphed it in multiple steps. And that's what we're talking about with a chain of functions. Okay? So I'm going to talk to you a little bit about specific problems on the homework. But before I do that, Mr. Herney, do you have anything to throw into any of this, or does that seem good?
Here's a fun fact of the day for you. This would be a corner. This would be a cusp.
Yep, that's another reason.
Fun fact of the day. Here it's like curvy and then comes to a jagged point. Here it's like two things that are linear coming to a jagged point. That's really the difference.
All right, so specifically for the homework as you guys are going through and doing the homework, okay? So the beginning is where you're doing all the words. So remember that you might have some that are product of two continuous functions is continuous instead of being a composition. Or maybe it's just a function you recognize. Like number 6. I think number 6, whatever your rule is, and however it's defined, I'm just going to write f of x because I don't know. I think it's this, big square root of 4 minus x squared. Because don't forget how to graph that. You just had that on your last test or something similar to that. If you have a perfect square minus x squared and it's underneath the radical, isn't this the top half of a circle? So when you're giving me the sentences of how to break it down to prove that it's continuous, yeah, you're going to want to do like the inside is 4 minus x squared, which is a polynomial. Polynomials are continuous everywhere. And then you're going to want to say the outside, whatever letters you use, equals just the square root of x, and square roots are continuous within their domain. And then you're going to want to put it back together and say the composition of two continuous functions is continuous. But when you do the graph, you should know that it graphs the top half of a circle. We just did that. So I'm reminding you of that so you don't get stumped on number 6. Okay? Number 4 and number 7, which I was already talking about number 7, I think those are the ones that they're products of two continuous functions. And products of two continuous functions would be continuous. And those two you're going to graph on your calculator. You can't do the whole graphing with the chain of functions idea, and it's not going to be anything that you recognize what to do graphically. It's not a transformation. Like I said, I think one of them is like x times the square root of x. Okay, so those two be okay with the fact that you're just using the technology. Number 3 and number 8 are the ones that you end up graphing using that chain of functions idea, where you're going from inside out like we just did on those last 2 examples. So like when you do number 3, you do all the words, and then it like matches up with whatever problem it would be, 13 maybe, where you make the graph of it. And then when you do number 8, you do all the stuff with the words, and then when you graph it, that lines up with, I think, number 18. Okay, or however it works. So those 2 you're going to graph using that idea of that inside out chain of functions. Okay? So it just gets you good at the vocabulary, stating functions, and then this new idea about graphing. All right, we're out.